You have watched my previous YouTube shorts on artificial neural networks and activation functions. You might be interested in how the math inside the artificial neural networks work. So today let's deep dive into the math inside the artificial neural networks. First, I would like you guys to observe this basic math equations. A is 2, B is 3, C is minus 4. So D is basically the product of A and B, which is 6. E is D plus C, which is 6 minus 4, which is 2. F is E squared, which is 4. Now what I have done is taken all of these expressions and wrapped them in a value wrapper. Why I have done this, you'll notice it very soon. So first, after doing the very same operations, there is no difference in this. What I've done is called a draw dot function, which I've written above, which is a GitHub code that you can also copy. So draw dot f basically helps us visualize these expressions, and that is exactly why I wrap them in a value wrapper. So if you notice, A is 2, B is 3, these are the same values that we have given here. It is just helping us visualize. So D is the product of A and B, E is the sum of D and C, and E squared is F. Now you'll also notice that there is a gradient attached to each of the variables. What is gradient exactly? That is really what the point of this video is. So right now, as of now, the gradient of each variable is 0, and it should not be 0, because what exactly is gradient? So gradient tells us how a particular variable is being affected with a very differential change. So let's say I change f by 0.001. I add 0.001 to f. How will f be affected? F's data will be 4.001. So obviously, if I just add any differential amount to f, the difference will be the very same differential amount. That is why the gradient of f is 1, because f is directly proportional to itself. But let's see what will happen if we change e by a differential amount. Then it won't be directly proportional, because we see f is e squared. If you remember your calculus classes, if we differentiate x squared with respect to x, we'll get 2x, right? Like ddx of x squared is 2x. So if we differentiate, like we know f is e squared, right? So if we differentiate df by de, we'll get 2e, right? Therefore, the gradient of e is 2 times e, the data of e. So 2 into e is 4. That is why the gradient of e will be 4. So any differential amount of change in e will affect f 4 times, and which is very obvious because it is just squared. Now let's see how does these variables c and d affect f. So what we'll do is we'll do the same operation. We'll differentiate f with respect to c and d. Differentiating f with respect to c and d is quite complex because we have a middle variable here, e. So what we'll do is, we can't do df by dc or df by dd directly. What we'll do is we'll break down df by dc into df by de into de by dc. What we have done here is df by dc is df by de into de by dc. As you can see, we have just breaking df by de into de by dc. Now we know that df by de, which we have already found out, is 2 times e. Therefore, df by de is already found out, and de by dc. What is de by dc, guys? So if we look at this, if we differentiate, e is b plus c, right? So if we differentiate e with respect to c, we'll get 1, right? Because c is constant, so it will be nulled, like it will be 0, and differentiating c with respect to c will be 1. So differentiating e with respect to c will give us 1. That is why df by dc, which is equal to df by de into de by dc, is 2 times e into 1, which is 2e, which is equal to 4. Same goes for de by dd, because it is just the same, because it's addition here. So here also it will be same, 2e into 1, which is equal to 4. So even here the gradient is 4. What I want you guys to remember is, when there is a addition in between, the gradient simply travels back. There is no change in gradient whatsoever. Apart from that, let's see how the variables a and b affect f. So we'll do the same operation again, df by da and df by db, but we can't do it directly. So what we'll do is we'll break it down into df by dd into dd by da. We know d is a into b, so if we differentiate D with respect to A, we'll get B. As we know from the product rule, A will be 1 and B is a constant multiplied to 1, so B will be left out. So differentiating D with respect to A will give us B. So df by dA equals to df by dd, which is already known to us, which is 4 times B. What is B? 3. So 4 into 3 is 12, and same goes for differentiating with respect to B. We'll get A. So df by dB is equal to df by dd into dd by dB, which is equal to 4 into A, which is equal to 4 into 2, because the data of A is 2. So we get the gradient as 8. So if we call f dot backwards, machine learning guys will know what backwards does, but here what I'm showing is what is the internal calculations going on when we call f dot backwards. F dot backwards will basically set these gradients for us automatically, which we calculated manually. Draw dot f, this time calling this, will change the gradient. Gradient of f is 1 as we calculated, gradient of E is 4, gradient of C and D is basically transferred back from E, there is no change, and gradient of A and B is 12 and 8 as we have calculated. This is exactly what we calculated. I'm kind of proud of myself, but let's go ahead. First, so basically you might be thinking, what does gradient exactly do and why are we calculating gradient at all? Because as I told you guys previously, that gradient helps us understand how a variable will affect the final output in a equation. So when in machine learning and in artificial neural networks, how it works is, all of us know that there is a forward pass that is calculating the loss, and then there is backward pass. So what happens is, first there was forward pass where the data was calculated, this was forward pass going forward, and this was the final output that was calculated. The loss, if this was an artificial neural network or this was a machine learning model, the loss must have been calculated, and then there was loss dot backward. Instead of f dot backward, there would be loss dot backward, and that will set gradients for all of these variables. Now all of the data of these variables will be changed according to the gradient. It will be more like E will be subtracted 0.001 times its gradient. So the data inside each of these nodes will get subtracted by a tiny amount of its gradient, and that is how the weights, when we say that the weights inside the neural network or artificial neural network is getting adjusted, this is what is happening. The weights are getting subtracted by their own gradient by a very differential amount, like 0.001 times or 0.1 times by its gradient. So this is what is going on. This I have taken another example, and this is just to show that this is one single neuron. So let's say x1 and x2 are input to a neuron, w1 and w2 are the weights, and then x1 and w1 is the product of x1 w1, x2 w2 is similar, x1 w1 and x2 w2 is the sum of these two, and bias, we just add the bias to x1 w1, x2 w2, and the final output is here. Now if we do draw dot n, we'll get w1 x1 w2 x2. Okay, sorry, we have, okay, this will be w2 x2, but whatever, we'll change it later. W2 x2, and this is the product, and adding the bias to it will give us the output. This is one single neuron. There will be a ReLU or sigmoid or tanh, some kind of activation function here, and then if we call n dot backwards, the same operation that we have done here will be done here also, and the gradients will be set as soon as we do n dot backwards. Draw dot of n will help us visualize it. Gradient of n with respect to itself is n, obviously. Now as we know from the addition rule that the gradient simply travels back when there is addition in between, so the gradient of bias and x1 w1 x2 w2 is also 1. Again there is addition, so the gradient simply travels back, but in multiplication the rule is simple. The gradient is multiplied to the data of other variable. So x1's gradient will be w1's data multiplied to the gradient of this, and similarly x1's w1's gradient will be x2's data multiplied to the gradient. So 2 into 1 is 2 and 1.5 into 1 is 1.5. So similarly we'll calculate here, x2's gradient will be w3's data multiplied to the gradient. 1 into 3 is 3, and w2's gradient will be x2's data multiplied to the gradient, which is 0. Now we'll also see how the data or the weights are readjusted inside a neural network during the backward pass in the future videos. That's it for today.